So is it graph theory question? Cool. Whoa. Oh, the number of edges. Oh, really? Oh, I see. Because then, yeah, because it looks like if it was a cube, then it looks like each face of the cube has like a four-sided guy, but then the vertex of the cube has like a triangular pyramid. That's pretty cool. What did they call that shape? Wow. That would be pretty cool to make a lamp out of. Too bad we couldn't have like math club and make one of those lamps. Oh, really? That's pretty neat. Okay, I'm just trying to post this link on the website for the YouTube stream, and then we will get started. Oh, there it is. That's really something else. So today, by popular request, we're gonna sort of take a bit of a diversion. So we're gonna take a look at Euler's formula, which is gonna be, I hope it'll be fun. I think it's pretty neat. So what we're gonna do is we're gonna kind of go back and forth into Desmos a little bit, and I'm gonna see if we can derive this formula, because we have pretty much everything that we need to derive Euler's formula. And if you weren't sure what Euler's formula is, well, it's kind of so you may have seen this before. You may have seen that like e to the I pi is equal to -1, right? You may have seen that formula. This is like one expression of Euler's formula. So Euler's formula in general is that e to the I times x is equal to cos of x plus I sine of x, where I is equal to the square root of -1, or in other words, you can also say that I is the unique number such that when you square it, it's equal to -1. You've probably heard of I. It's called the imaginary number, and we really only need it like a little bit in order to solve this. We really just kind of need it at the last step. But we have pretty much everything that we need to go ahead with deriving this formula. So this is kind of a bit of a diversion from our textbook, but I think it's worth it because it's kind of fun, and we have a long weekend coming up. So I think it'd be kind of nice if we did this, and then that way you can kind of catch up on other homework. I'm not going to assign new homework today to give you a little bit of a break. And yeah, so we'll just take a look at this formula. I mean, it's not like this is easy. This isn't an easy formula to derive, but I think it'll be maybe a little bit fun. So, oh yeah, it looks like we got a lot of people here now, so that's great. Okie dokes. So I'm going to get started on this. So the first thing that I want to do is like the reason why we're able to do this now is because this formula is based on the power series, or in other words, the Taylor series expansion for each of these formulas. The exponential function here, so it looks at the Taylor series expansion for this. It looks at the Taylor series expansion of this, and then this as well. And that's how we're able to get this formula. So what I'm going to do is I'm going to sort of assume that we're able to calculate these Taylor series formulas ourselves. I think that they're probably already in the textbook in terms of their like being a question at some point. Yeah, it's got to be somewhere in here. Yeah, I think that, yeah, on page 486 we do sine of x. You know, maybe we actually, yeah, on 468 and 469 they do sine and cos of x, and then on 467 they do e to the x. So what I'm going to do is I'm just going to say, so see page 4, what is it, what did I say, 467, 67, 468, and 469 for the following derivations. Okay, so, and those derivations are the following. Let me just sort of copy them out. So that basically what I'm talking about is we need the Taylor series expansion of, well, we'll start off with e to the x, and that's on page 467. I'll just make a little arrow here. That's on page 467. And then I think the next one is sine of x. Yes, sine of x is on 468. So sine of x. Pardon me? Yeah, they're just proofs, and I'll do one of them, and you'll see what I'm talking about. It's quite straightforward. You should be able to do it yourself. I mean, like, we're talking about the Taylor series expansion of like sine of x, and that's what I would consider to be like an elementary question. Whereas in your textbook, like, you're asked to find the Taylor series expansion for things like the natural logarithm of 1 plus x, or sine of x plus cos of x, right? So those are a little more tricky than just sine of x, right? So and then cos of x, I believe, is on page 469. Okay, so I'll do one of these just really quickly, just to give you an idea of what I'm talking about. So first of all, so let's do just one. I'll do it in green here. Let's find the nth Taylor. Should be a capital T. Taylor series expansion for let's do e to the x. Actually, let's do sine of x, because e to the x is almost too easy. So let's do sine of x. Okay, so the first thing that we would do is we would say, okay, well, first we set f of x to be equal to e to the power of x. Okay, then we say, well, f prime of x is, oh, what did I say? Sine of x. My bad. Okay, so that means that f prime of x is equal to, well, the derivative of sine of x is cos of x. And then the second order derivative is f double prime of x, which is equal to negative sine of x. And then the third derivative is going to be negative cos of x. And the fourth derivative of x is, or of f of x rather, is, now we're back to sine of x. And if we keep doing this, we'll find that we get this loop happening, right? So we can kind of stop there and kind of say, okay, well, there's a pattern going on. So let's start calculating these points at 0, these functions at 0. So we'll evaluate each of these functions at 0. So f at 0, well, sine of 0 is 0. F prime of 0, well, that's cos of 0. Cos of 0 is 1. F double prime of 0, well, that would be negative 1. F triple prime at 0 is, oh, sorry, not negative 1, negative 0. Come on, you guys need to be paying attention. You should correct me. f triple prime of 0 is -1, and then sine of 0 is, oh, we're back to 0 again. So the fourth derivative evaluated at 0 is equal to 0. And I should say the Taylor series expansion for sine of x evaluated at 0. So in other words, we're looking for the Maclaurin polynomial. Okay. So you can see that it doesn't really matter how many times we do this. We're gonna get this cyclic pattern. So this pattern repeats itself. So the pattern repeats itself every 4 derivatives. Derivatives. Okay. So what does that mean? Well, let's see if we can find the let's find the nth. I keep calling it Taylor with a lowercase t. The nth Taylor polynomial for sine of x is the following. Well, let's call it p sub n of x. Actually, just I know like this might sound kind of annoying, but I'm going to turn this into a k. It's just going to work nicer if we use a different letter than n. And you'll see why in a second. I mean, it's just a matter of preference. I just like it better when it's k. Mostly because I have that already plugged into Desmos. So you'll have to bear with me. Okay, so the kth Taylor polynomial for sine of x is the following. Well, we'll take this first one. It's 0 over 0 factorial times x to the 0, right? Plus 1 over 1 factorial times x to the power of 1 plus, what is it? 0 over 2 factorial or times x to the power of 2 plus, what is the next one? -1 over 3 factorial x to the 3, and we can keep going. And because we have this nice cyclic little pattern going on, right? It's basically this pattern, except the only thing that's changing is the factorials. So we get like a 0, 1, 0, -1, 0, 1, 0, -1 as our coefficients, or at least the numerator of our coefficients. The denominator of our coefficients are just going up by 1, right? So we're going from 0 factorial to 1 factorial, 2, 3, 4, 5, and then our exponents are going up by 1 as well. So this is going to be really easy to express as a sum using summation notation. So I'm assuming you guys have seen summation notation before. Is that true? Yeah? Okay. I don't want to be the first to introduce it to you. If you need a little bit of clarification as to what these symbols mean, just let me know. So here's my sum. So here I am going from n equals 0 to k. That's also why I chose to switch that letter to k, because I like using n as my index, because the other option is to use I as your index, but we're going to be using the imaginary number I in a little while, so I don't want to be using I. So I'm just carefully picking my letters. So that means that we can express this as a sum, like without too much trouble. This sum is going to be, well, I've got the sum from going from n equals 0 to k, and this like the first thing to notice is that well, we got a whole bunch of zeros here, so those just sort of cancel out, and so yeah, that's the first thing to notice. Here, I'll put that in red so you can really see that those are canceling out. So the only like terms that we really see are, they're all going to be odd, right? They're all going to be odd. So I've got 1, 3, the next one, like you can see that the fourth term over here, that's going to be 0, so the fifth term would be back to +1. So I've only got these odd numbers, so I've got 1, 3, the next one would be 5. And then within those odd ones, we're going back and forth between positive and negative, right? So we've got a plus sign here, we've got a minus sign here. So I'm going back and forth between positives and negatives. So the way we can write this one out is by saying that this is, okay, well, I'm going to say it's negative 1 to the power of n. And what that does is it tells us, okay, on our first term, our very first term, I'm going to have that n is equal to 0. So I've got negative 1 to the power of 0, which is positive. So this part right here is just telling us that we're going back and forth between positives and negatives. So our next term over here, when n is equal to 1, we're going to have negative 1 to the power of 1, which is negative. So that'll make sure that this is negative. Okay? So now I've got my pluses and negatives going on. Now I have to make sure that my terms are just, I'm only going to see odd numbers, right? Because I only see odd numbers here. Right, I have a 1 factorial and I have a 3 factorial. I have an exponent of 1 and an exponent of 3 here. So the way I can do that is by, well, I'm going to have my fraction. The numerator of my fraction is just going to be x to the power of 2 times n plus 1. It's 2n plus 1 because on my first term, I'm saying that my index starts at 0. So when n is equal to 0, I've got 0 plus 1, which gives me this one right here. Okay? And in the denominator, I'm going to have pretty much the same thing. I've got 2n plus 1 factorial. Because we should have the same thing here as here, because in each of these terms, I've got the same thing as my factorial as my exponent, right? So I've got 1 factorial and an exponent of 1. Here I've got 3 factorial and an exponent of 3. So there's my power series, my Taylor polynomial for sine of x. And that's the kth one. That's the kth one. Go ahead. True. Yeah. So, yeah. Mm-hmm. Yeah, that's a good point. That's a good point. So if you didn't catch that, if you're watching on YouTube or what have you, so this wouldn't actually be the kth polynomial. This would be p sub 2k plus 1, that or 2k plus first polynomial. That's what that would be equal to. In any case, the main idea is that this is the Taylor polynomial for sine of x. So regardless of where we stop, what's interesting is that as k gets bigger and bigger and bigger, our approximation gets better and better. So what I did, oh, go on. Mm-hmm. Yep. Mm-hmm. Oh, okay, right. All right. So the idea is that we're skipping over those terms. So the question was, so how does this 2n plus 1, how does this 2n plus 1 work, especially when we have terms that are 0? How do we get 0 out of this? Well, the idea is that we're just skipping over them. Okay? So when here, why don't we actually write out this this expression down here, kind of like the long version of it. So let's say that n is equal to 0, because that's where we start. When n is equal to 0, we've got negative 1 to the power of 0 times x to the power of, well, 2 times 0 is 0 plus 1 is 1. So we get x to the 1 over, well, 2 times 0 plus 1 is 1 again on the bottom, so we got 1 factorial. So that's our first term, which is good, right? And negative 1 to the 0 is just 1, so let's actually just erase that, right? When n is equal to 1, so that's my next term. When n is equal to 1, hopefully we get this guy right here. Like we're going, oh, sorry, not that guy here. So this is our first term. We skip the first one here because it's 0. Our first term, when n equals 0, we get this one. When n equals 1, the goal is that we get this one here. Okay? So when n equals 1, let's see what happens when we plug this in. So I've got, negative 1 to the power of 1 times x to the power of 2 times 1 plus 1. Well, 2 times 1 is 2, plus 1 is 3. So I've got x to the 3. And again, 2 times 1 plus 1 is 3, so I've got 3 factorial. And that's exactly what this term is, right? It's negative 1. Here, I'll just write this as negative 1. Negative 1 times x to the power of 3 over 3 factorial. The next one, when n equals 2, maybe you can see what's happening here. Well, I'm going to get negative 1 to the power of 2, which is just positive 1, so I don't even have to write anything. I'm going to get x to the power of, 2 times 2 plus 1 is 5. And again, 2 times 2 plus 1 is 5, so we got 5 factorial. So that's what the next term would be. Because the one after this would be 0, right? I would get 0 over 4 factorial times x to the 4. And the one after that would be positive 1 times x to the 5 over 5 factorial, which is what exactly, yeah. So the whole idea is that we're not trying to make our expression equal 0 ever. We're trying to get it to skip over the terms that are 0, right? So we're skipping over those 0 terms. Okay. Okay, so that's the power series, or the Taylor series expansion for sine of x. And what I'm going to do, just to make things a little bit easier, because we could spend like all day sort of bogged down with the details. I'm just going to tell you what the rest of them are, and then we'll sort of take a bit of a survey and take a look at all of them and see how they're similar. So certainly we have sine of x. This is the one that we just derived. So sine of x. I skipped over a step. I want to show you these things on Desmos. So I'm going to. Actually, no, we can do this. We'll go to Desmos in just a second. We'll write them all down. So sine of x, it turns out, is the sum where n goes from 0 to infinity. So this works for like we can keep going and going, and the higher our value of k is here, like this k right here, the higher the value of k, the more and more accurate that we're getting. So if we take the limit as k goes to infinity, then we actually get an exact value for sine of x. So we can actually write this as an infinite sum, and that would look like this. So I would have basically the same thing, 2n plus 1 over 2n. Oh, I forgot the minus 1 to the n. Pardon me. Minus 1 to the n of x to the 2n plus 1 over 2n plus 1 in brackets factorial. So that's what sine of x is equal to. It's actually equal to that. So it's the limit as k goes to infinity of this thing, or in other words, we'll just have that upper bound be infinity. And then let's look at sine of x, or sorry, cos of x rather. So cos of x, that's equal to the sum as n goes from 0 to infinity of, again, negative 1 to the power of n. And we have, in this case, x to the 2n over 2n factorial. I'll make that fraction line a little bit nicer. And if you don't see that immediately, you can go to, what was it? What did I say? Page 469. Page 469 has this derivation. So I'll just write those numbers down. So page 469, this was 468, I think. Yeah, page 468. All right, page 468. And then let's take a look at e to the x. And I'm just for, like, usually I call it e to the x. For this exercise, I prefer the functional notation for this. So I'm going to call this exp of x, okay? Because I want to be very clear that these are all functions. Okay, so if you've never seen this before, this means e to the x. But just for this exercise, I want to be using the functional notation, so I'm going to be calling it exp of x. And then this one's very straightforward. If you remember, this was one of the ones that I think was on the worksheet that I gave you a little while ago for Mr. McIntosh. And the idea here is that the the derivative of the exponential function is always going to be the same, right? So when we're doing like this portion of the Taylor series expansion, we're going to get a whole bunch of ones, because we're going to have, like, if this is e to the x, then all of these are going to be e to the x, right? Because whenever you take the derivative of e to the x, you get e to the x. And e to the power of 0 is 1, so we get a whole bunch of 1s here. So when we actually calculate the polynomial, all of these are going to be 1s up here. So that's what's happening here. So we don't get any negatives or positives, so we don't have to worry about anything like this. So the Taylor series expansion is just x to the n over n factorial. It's the easiest one to remember. It's basically like the vanilla Taylor series. And I should also say that this is going from n equals 0 to infinity. Okay, so these are actually equal, and I know that I'm kind of waving my hands here, because the next section that we're actually supposed to do talks about like when you can go to infinity. So if you're a little confused as to like what this is meaning and like these equal signs, that's okay. I am kind of skipping over a little bit of work that we will attack next week, but the gist of it is that the bigger we get, the closer to the actual function we're getting, and as we take the limit, these two things end up being equal to each other. So now I'd like to bring us over to Desmos, and I'm just going to quickly do one more thing. 2 to the n of n factorial. Okay, awesome. And I'm going to hide that. Okay, and then I will have cos of x, or e to the x. Okay, so, oh yeah, I have to show you my screen now. Open up OBS, and hopefully you can see it. Can you see my screen okay? Yeah? Okay. Okay, so here, let me hide some stuff. So I've gone ahead and I've drawn e to the power, sine of x here. That's what's in red. So I can hide it and show it. I also have cos of x and e to the x. And along with that, I have underneath that their Taylor series expansion, and it's going just to k. So k is the upper bound of this sum. So if you take a look at sine of x and then take a look at the Taylor series expansion, you can see, like, when k equals 1, like, it actually does look pretty close around 0, but as we increase k, you can kind of see what's happening here. It's getting closer and closer, further and further away from 0. And if you think about it, Desmos is actually doing quite a bit of work here. Like, it's pretty amazing, the numbers that it's calculating here. Like, let's think about the numbers that it has to calculate to graph this. We've got k equals 39. Okay, so 39 shows up in here. So n is going from all the way from 0 to k, which means that we have to let's think about this number right here. We have to calculate 1 factorial, 2 factorial, 3 factorial, 4 factorial, all the way to, what is that, like 2 times, well, let's make it easier for ourselves. So this would be 2 times 40, which is 80, 81 factorial. Like, that's a huge number. Like, let's take a look at what that looks like. 81 factorial. It's 120 digits long, right? Like, it's a huge number. So it's quite impressive that that Desmos is calculating all of this in real time, because these are huge numbers. Exactly, yeah. So not only is it calculating 81 factorial, it's also calculating 80 factorial, and 79 factorial, and 78 factorial, and not only that, but it's plugging that in to like x to the power of whatever, right? So this is quite an incredible piece of software. I just want to bring that up, that there's a lot of stuff going on here. So I wanted to just like have my slider go all the way up to like 1,000 to see what it would look like. But as we get to like 50, it kind of just stops chugging along, and it's actually doing a pretty good job, right? Oh yeah, here we go. I don't know if it shows up in the stream, but it's looking kind of a little bit broken here. So it's not very happy. Like you can see, they must be doing some kind of like estimation here, because this is not looking so good. Either that. Oh, go on. Yeah, that does not look differentiable at all. But I mean, it could also be, and this part I'm not actually sure about. It's possible that like maybe that's actually what the function looks like, right? Like maybe it isn't actually supposed to be like a smooth line. Maybe it is actually kind of like super wavy like that, and they're just sort of getting a little pixelated because there's a lot of curves. So anyway, looks like oh, here we are. We're back. So so that's sine of x. So cos of x is going to be this one. So here's the actual cos of x, and then this is the Taylor series expansion, and it's got the same slider here. So it's looking pretty nice. So yeah, that looks a lot like cos of x. And then here's e to the x over here, the function that we all know and love. And here is this one, and this one's much easier to calculate, right? Because I mean, 50 factorial is much smaller than 80 factorial. Like it's way smaller. So this is much easier to calculate. So yeah, I thought it was pretty neat to be able to see all of these. And maybe you can kind of get the idea that as k gets bigger, like you can imagine that limit going off to infinity, and then you would actually have the function that you want. And that's something that we'll be talking. Oops, that's something that we'll be talking about next week. Anyways, I just wanted to show you that. So back to my iPad screen. There we go. Okay. Okay. So where were we? Just gonna bring this up. Okay. So these are the three Taylor series that we have, and you might notice something. Oh, and this one was this was on page 467. Okay, so you might notice something that's going on here. If we were to like take a look at this, like this guy right here, this is like all numbers. And what I mean by that, or I should say all like counting numbers. Okay, so like this one doesn't skip over anything, right? Like we have, like we're gonna see in the denominator, like let's just think about the factorials that we'll see. The factorials that we'll see, like who cares about the exponents and all of that? The factorials that we're gonna see, we'll see like, we'll see 0 factorial, we'll see 1 factorial, we'll see 2 factorial, 3 factorial, right? We're incrementing this factorial by 1 each time, right? And similarly, we're going to see the same thing when in the numerator. We're going to have like x to the 0, we're going to have x to the 1, we're going to have x squared, we're going to have x3, right? X3, I mean x cubed. So we see like all of them, and they're all positive, right? They're all positive. So that's what's going on with the exponential function. Whereas with cos of x, over here, we don't see all the counting numbers. We see all even numbers, right? We see all the even numbers. So like in our Taylor series expansion, what we'll see is like forgetting about the odds and the evens, and, or sorry, sorry, I didn't mean that. I mean the positives and the negatives, forgetting about the positives and negatives, and just looking at the factorial. What we're going to see is we're going to have, well, 0 factorial, right? Then we'll have 2 factorial, and then 4 factorial, and then 6 factorial, right? Because we're going up by 2s, but like because n is our counter, and we're multiplying our counter by 2. And then we'll have similarly, we'll have x to the 0, x to the 2, x to the 4, x to the 6. And then if we want, we can start worrying about pluses and minuses, right? It's going to look something like that. Whereas sine of x, we get all the odds. So this is all odd numbers, right? And just like that, and we get some alternating pluses and minuses and that. But this is going to be like all the odds. So in the numerator, we're going to have a 1. We're going to have a 1 factorial. We'll have a 3 factorial, a 5 factorial, a 7 factorial, right? And then in the numerator, it'll be x to the 1, x to the 3, x to the 5, x to the 7. And now we can start to worry about the pluses and minuses. So we'll have a minus out here. Oh, sorry, no, that's a plus rather. So, and we've got a minus here, and a plus here, and a minus here, and a plus here, right? So these are like pretty similar. It would be pretty nice if we could combine the sine of x and the cos of x. Like if we could kind of squish this into one, right? And then maybe we could get something that is the exponential function. And that's what Euler did several hundred years ago. Is he saw this pattern and he said, okay, well, these are like really, like if I could add these two together, I almost get this. Like it's very, very close. But the problem is, like the only thing that's in our way are these negative symbols. Like if there weren't any negative symbols, then we would get e to the power of x. But the problem is we have those negative symbols. And I know it's 156, and I'm almost done. So I might go over time just a little bit. But yeah, okay, so let's see what happens when we take the exponential function, and instead of finding like exp of x, let's multiply x by I and see what happens. Well, this is going to be the sum. This is going to be the sum where n goes from 0 to infinity of, well, we'll have 1 over n factorial times, and instead of x to the n, now we have I times x to the n. And just to be very clear, I is a special number whose has the property that I squared is equal to -1. So we're gonna use this to our advantage here. And this, believe it or not, is going to introduce the negatives in all the right spots. And it works out very nicely, and it's very satisfying how the negatives just perfectly land where we want. The only problem is that we're gonna have like a leftover I, and that's where the I comes into our formula. So setting this aside, we have that this is equal to, well, let's like expand this out and see what we get, and see if we can figure out how to go from there. So I've got, well, the first term is just 1, right? Because when n is equal to 0, the exponent is 0, so whatever, we just get 1. The next term that we get, when n is equal to 1, well, we have 1 over 1 factorial times I x to the power of 1, okay? So I, like there's no i's to sort of cancel out, I is just there. So we may have to sort of tidy this up a little bit, but that's okay. Next term that we get is when n is equal to 2, so I get 1 over 2 factorial times I x squared. Okay, so look at that. Now we have an I squared, so that's going to give us a minus sign, which is kind of nice. Next term we get is 1 over 3 factorial times I x cubed. Good. After that, we have 1 over 4 factorial times I x to the power of 4. And I think let's do one more. Let's squeeze in one more. In the notes that I did earlier, I did 6, but I think 5 is fine. So we'll go up to 5, and that's I x to the 5, and then I'll write just ... Okay, now let's start cleaning this up, and I'm going to do some color coding, and you'll see like I'm kind of purposely thinking ahead, but I'll do some color coding which should help. So every second term I'm going to do in red, and the other terms I'm going to do in blue. So this first term is 1. This next term is in blue. So I've got, okay, well this I, I'm going to factor this I out. So I've got I times 1 over 1 factorial times x to the power of 1. Okay, now in red, okay, look at this. Now I've got I squared. So I squared is equal to -1. So now I'm going to write minus 1 over 2 factorial x squared. Okay, so really all I'm doing here is I'm just taking care of the i's. This next term here, I to the power of 3, that's I squared times I, or in other words, that's negative I. So I to the power of 3 is equal to negative I. So in blue, now I've got minus I times 1 over 3 factorial x to the 3. Okay, now in red, I have, okay, well, here I to the 4 is equal to, well, I squared times I squared, which is equal to negative 1 times negative 1. Okay, and that's equal to positive 1. So now I'm just back to positive. So I've got 1 over 4 factorial times x to the 4. And in blue, let's see here. So here I've got I to the 5. And, well, I to the 5 is equal to I to the 4 times I. I to the 4 we saw is 1. So this is equal to I. So I to the power of 5 is equal to I. And that gives me plus, and so it's positive, so it's plus I times 1 over 5 factorial times x to the 5. And we can keep going and going and going, but hopefully we can start to see enough of a pattern. What I'm going to do first is I'm going to collect all of my red terms. So that's going to give me 1 minus 1 over 2 factorial times x squared plus 1 over 4 factorial x to the 4 plus, and you can probably see what the pattern is, right? We get all of our even terms with alternating pluses and minuses, which hopefully we can recognize. Now, the blue terms all have an I in them. So every second term, we're going to have I to the negative power. Or sorry, not to a negative power, to an odd power, which leaves us an I. So what I'm going to do is I'm going to factor out an I. So I'm going to factor out an I from all of these terms. And what I'm left with is 1 over 1 factorial times x to the 1 minus 1 over 3 factorial x to the 3 plus 1 over 5 factorial x to the 5 plus dot dot dot, and I'm kind of running out of room. That's my bracket. Okay, it's kind of a funky bracket, but you get the idea. So hopefully we can recognize these. This right here, this is cos of x. And this right here in blue is sine of x. Okay, so this is cos of x plus I times sine of x, or if I want to write it a little bit more nicely, and maybe I'll go back to green, I've got cos of x plus I sine of x. And that's what e to the x is. So yeah, there it is. So cosine, sine, and the exponential function are, oh yeah, e to the I, yeah, there, thank you. So the exponential function, I was trying to copy that. The exponential function, the cosine and sine functions, they're all intertwined and they're all kind of part of the same big picture. So if we really want to just see like the huge beauty of this, I've got one more thing to show you, and I know that this one's maybe going off on the deep end a little bit, so just bear with me. Okay, this is going to take like 5 minutes tops. Okay, so there's a little thing called the complex plane. Okay, and it's a way of graphing complex numbers, and it works just like you would have with just like the Cartesian plane with like x and y, except instead of an x and y plane, you have a real an x and y coordinates. You have a real coordinate and you have an imaginary coordinate. So anything that has a factor of I in it, that's like your y, your up and down, and anything that has a real that has no imaginary factors, it's just your x coordinate. So if we were to sort of graph this, okay, well, we'll have a graph that looks something like this. So it'll be -1 and +1 over here. Over here we're going to have positive I and negative I. Well, if I were to say that, okay, e to the I times x is equal to sine, or I times sine of x plus cos of x. Well, what that is like sine of x plus cos of x, like if I think of this as my y coordinate, and this is as my x coordinate. And instead of maybe thinking about this in terms of x, because we're dealing with sine of x and cos of x, maybe if we used a different variable like theta, maybe we would see that, oh yeah, well, now we're just talking about angles. This gives us a unit circle around, like in the complex plane. So if I were to say, okay, here's an angle of theta, this point right here, that according to our formula is the point, well, our x coordinate is cos of theta, and our y coordinate is sine of theta. So really, like it's the coordinate. So yeah, if you wanted, you could say, yeah, it's I sine theta. Yeah, and that's fine too. And I'm going like probably like a school year every minute in terms of like the rate of education that I'm like expressing these things in. But I just thought that this was cool, and we can, like, we're almost there. So the main takeaway is that if I take e to the I and I multiply that by pi, I get I times sine of pi plus cos of pi. Okay, and that's this point right here. That's what that point is. And I could find any of these points. I could figure that out using this formula. I would just have to plug in that version of theta. But this one is easy to calculate. E to the I pi is equal to I times sine of pi. Sine of pi is 0. And cos of pi is, oh, I shouldn't say that. Cos of pi is -1. So e to the I pi is equal to -1, which is so cool. Yeah, there you have it. So I know that we're kind of going off script here a little bit, and that this isn't super relevant to like your AP exam, but you know, it's right before a long weekend, and there were some requests to see this. So I hope that you're not too upset with me for, you know, wasting your time or anything. I hope you don't think of this as a waste of time, because this is a formula that's been sort of honored, and everyone has loved this formula for several hundreds of years. So I think it's worth it to you know, take the time to see this formula, because maybe I don't know, maybe this is your last year studying math. Maybe in university next year you end up, you know, going through the humanities or something like that, or maybe you do some sciences that don't require a lot of math. It'd be a shame that you're so close to seeing this amazing, incredible, beautiful formula, but don't get to see it. So just think of it like that we had a great opportunity to do something today, and we jumped on that opportunity. Yeah, there you go. Maybe we'll do partial differential equations tomorrow. Yeah, there you go. Yeah. No classes tomorrow. Yeah, tomorrow's Good Friday. But I will see you on Monday. So, okay, bye-bye. Yeah, so, yeah, I'm not going to assign any homework today. So, yeah, take care. And if you have any questions about anything, don't hesitate to ask. But yeah, okay, take care, guys. Bye-bye.